Thanks. Yeah, good afternoon, everyone. I hope, you will soon wake up from your, this sleepiness from after lunch. Okay, so first of all, I would like to thank the organizers, all of you, for putting up such a nice and wonderful conference. This is me, Tapan, and and I'm going to talk about some active particles which have peculiar characteristics like non-axisymmetric, flexible. Those kinds are Sunil already talked about, but our swimmers are slightly different, and then we'll see how that goes on. So the work that I'm going to present, that is mostly done with Direct. So my apologies to all of you who has visited his poster already, because clearly he is a better orator than me. But probably you will see a little bit of more movies here, okay? And those who have not visited, I request you, if you are interested, even after listening to my talk, go and encourage him. So these are some funding sources. And yeah, so I'm from IISc Tirupati, that's the institute logo. And this is my group at IISc Tirupati. So a few years back, I was in this group, Sriram's group. And if you have not recognized, this is me, plus the hair and minus some weight. Okay. And then I was looking for some logo to represent Sriram's group. I could not find it, and then thought that, okay, so I made it, and then I have not proposed it to the group, but I thought that this would be a nice logo. so, we'll discuss that within the group and then decide whether it can be a permanent logo. But approve? Okay, thanks. Yeah, thanks. Yeah, I did it. Okay, yes. Here, I did it yesterday. Okay, and good thing is that, feels like Sriram would be actually paying attention to the talk. Okay. Okay. So, yeah, so before I move ahead, happy birthday, Sriram, and thanks for everything. And echoing what Momita said, you not only taught us how to do research, at least you tried. I don't know whether I learned or not. But more importantly, you taught important lessons. That that shaped my academic career, academic life, even sometimes personal life. Okay, thanks for everything. Okay, so moving ahead, this is the work that the initial inspiration of the work came from this work from Yug and his collaborators. And this is very nice work where they considered a suspension of E. coli in a rather dense concentration. And then surprisingly, what it is observed that so these are some tracer particles, they move in elliptical orbits in a synchronized way. So that's the collective phenomena. But if you look at the individual cells, they look apparently random. Although if you average all of them, then again you see the elliptical rotation. Okay. So I think he gave the theoretical, so first-hand theoretical understanding, quite convincing. But we took the inspiration and thought that we'll just put on in hydrodynamics and see what can be seen. Okay, that's just the inspiration. And what we thought is that, so we have a model for a simplified model that I'll describe now for this bacteria. So this is turned on, right? Okay, yeah. So then we thought that in a dense suspension like this, there is a priori no reason to think that the flagella will not be bent somewhere. Okay, so if the flagella bends, the system becomes non-axisymmetric. So this is an axisymmetric example. Okay, so we, as Ramin told, so there are different approaches to talk about active matter. So we thought that we'll start with the bottom-up approach. But then later on also, I'll actually at the end, I'll tell you how we are actually thinking about the continuum limit, but just one sentence maybe. Okay, so this is the beginning. So we started to develop the model, but turns out that it becomes so complicated. And then we found that even the single particle dynamics is interesting. So then we found some in other motivations for continuing single particle dynamics. And this is one example. This is an experiment where an active particle called Clavinder is taken, which is fairly rigid and round. and they are taken in a channel where there is a flow that is imposed on that direction. And if nothing else is done, then the particles on an average move along the streamlines, and they are taken away, flown away by the flow. Okay, and then the initial concentration, if it is uniform, that remains uniform throughout the duration of the experiment. So what is interesting is that when they shine light on one side, so these particles like to orient along the light. Okay, that is their phototactic. So in that case, what is seen is that the particles are focused towards the center of the channel. So the explanation, the simplified explanation is that there is an interplay between the vorticity, that's the flow is parabolic because they are between two channels. So which means that there will be vorticity due to flow at every point along the channel. And if there is also a torque because of the aligning effect from the light, then there could be steady state orientations. Those are towards the center line if the particles are up, and towards the downwards if the particles are up, and if particles are down, then it will be upwards, which leads to this concentration, so focusing of the particles at the center. Okay, so this cross-stream migration, so this cross-stream migration, that is seen only in presence of externally applied orienting field. So if you don't have the light, then you don't see that. That is the observation there. Then a theoretical understanding was actually predicted even before the experiment from the group of Holger Stark and even Rafai, the same group, they also did some simulation. And then they see the oscillations. So this is the length along the channel. So the length along the channel. Okay, and then the particle trajectories are oscillatory. Okay, so this is what is seen here. If you don't shine any light, and if you shine light, and then you can see that either the particles go towards the center or they go towards the wall, depending upon whether you put the light there, upstream or downstream. That was the observation. And then a simple-minded theory was proposed from, actually, I should have mentioned that from this group, okay, Holger Stark group. This is their theory. The theory is that, so let's consider a dilute system, then think that, particles are not interacting with each other. Then each particle is like an active particle. So you can write down the velocity like this, and then the velocity will be partly due to the imposed flow and partly due to activity. So activity along is along the orientation E. Okay, so and then the orientation can rotate like this, and then the rotation have two influences. One is just this due to the vorticity of the flow that is applicable even for spherical swimmers. But if it is elongated, then it also experiences Jeffrey orbit. Okay, so if for spherical swimmer, that is not there. So which means that, okay, the oscillatory trajectory, by the way, is actually easily understood. Vorticity rotates the particle like that. They are moving because of the flow, but they are also rotating. Activity makes them move along their instantaneous rotation, which means that the effect will be like this. Okay, that's the oscillation. Okay, so the theory is actually that can capture even an elongated particle like this. And if they are even there, the oscillations are seen. Interestingly, without light, still on an average, it is still parallel to the center line, which means that no cross-stream migration. So the considerations here are the particles, active particles, they are rigid and symmetric. So apart from the fact that they are moving along their orientation, if you look at the physical shape, it's actually head-tail symmetric. That's the consideration. Therefore, the flow that is created because of activity, that is not coupled to its dynamics. Okay, that was the consideration there. And then, mostly it mimicked the experimental observation done on the LG. Now we asked, what if we consider a slightly complicated object which has a head-tail asymmetry? So head is different from the tail. And in that case, there is a possibility that the flow field created by the head might affect the tail and vice versa. So in that case, what will happen? That is what we asked. And they're interesting, that's not an irrelevant question. That's quite commonly observed in nature. And also, the question is it's applications basically. So in this talk, I would like to convince you Okay, that indeed this is not the full story. There are more to it. Okay, so hopefully I'll be able to convince. So to reach there, I mean, we moved in steps, and then if I'll go through it quickly. So if this is a microswimmer that is moving in a fluid which is a head and a tail, the simplest model for that is just a force dipole that Sriram always talks about. The one step ahead of that, I mean, so if you just want to, I mean, this will be like true when you are far away from the swimmer. If you move towards the swimmer, then you are going to feel the extended nature of the swimmer more and more. So we said that, okay, next the step would be just to introduce a cell body which is spherical. And let's say that this is the flagella force, which is still a point of force that is acting on the fluid. And the resultant force is acting on the cell body. That will eventually be passed on the fluid like that one. Okay, so that by our model, I just mean that this is the model we used in our work. Actually, Cristina, I mean, a few years back, already had introduced that model in a slightly generalized manner. And I mean, even finite size has been incorporated by many other groups. Ramin did that long time ago, and then some other groups near about our work. So what we did that calculation a little bit in an exact manner. But one of the calculation was to show the, I mean, if I take that model, then what will be the self-propulsion velocity? And this is the result. I mean, self-propulsion velocity as a function of the geometric parameter A by L. So on this direction, so which direction? So on this direction, I'm having a large L. So the physically what we can understand is that suppose L is large, then this point force will be far away. Then effectively this sphere will be traveling as if it is dragged by a dragged by a force, and that is this velocity. So we have this velocity. But as we imagine this point force to be brought nearer, farther and farther, nearer more and more, the flow field created by the point force will affect the velocity, and the net velocity will go down. Okay. So once you know this velocities, and then you can actually create the flow field around the object. There are various contributions. For example, the sphere moving in a fluid creates some disturbance. The point force creates some disturbance. The non-trivial part is that the point force is not isolated, but it is near a surface on which boundary condition needs to be satisfied. But we took some help of some, I mean, the mapping between Stokesian dynamics and electrostatics to come about the solution. And then the solution is actually, I mean, we did not solve it. This reference already did that. And then the solutions are that, I mean, so you have certain singularities which creates their own flows that is placed here inside the cell body, imaginary objects. And if you do that, then the flow created by them is exactly the flow that we are looking for, the reflected flow. Okay, so if you now add all these three parts, so those three flows look like that basically. And then if you add all three parts, this one, and then 1, 2, and 3, then you get the total flow field. And that is the exact flow field for the model. And some analogy with the experiment. I mean, so it's not very bad, I mean, given that how little we have put into. And once you have the flow field of a single object, then you can bring in other swimmers and then see the hydrodynamic interaction. And then those we have derived for our model. So that's the first part. Then, as I said, Direct started working on this. It's 3D. It's 3D, yes. Yeah. So Direct started thinking about this situation where the flagella can be bent. Okay, in general. Yeah.
So you didn't bring in the chirality of.
No, not yet. Yes. Yeah.
Wondering if that rotation which you showed in the beginning for the experiment.
So that rotation will not be changed, but chirality has a good effect. I mean, it's a good point. And Roman Stoker has an experiment where he showed that if you have shear flow, then a very strongly chiral particle would like to orient perpendicular to the shear plane. Okay, throughout our experiment, this analysis, we will assume that this particle is still parallel to the shear plane. And we have good reasons to believe that this will be for our case. Okay, we can discuss later on about that. Okay. So, yeah, any other question? Yeah, please.
Consider the chirality, will there be some kind of torque balance flagella and the cell
Right. So yeah, that's true. So if you introduce chirality, there has to be torque balance, but there has to be torque balance anyway because it's Stokesian dynamics. Okay, we are implementing torque balance, but when you have the helical flagella, you will have more components to it. Yeah. At the moment, we are neglecting, but I think for our case, actually, this is not a bad assumption. Okay, so this is the time that is left, right? Okay, okay. So this model, as I said, the bend model is non-axisymmetric, and luckily it can be broken into three parts, which is one is purely axisymmetric, one is purely non-axisymmetric, and interestingly, one active rotation comes. Okay, so that's the equivalence of that, and then we can solve for everything here. So it's a little bit non-trivial this part, but that can be also solved combined together. This is the flow field. I mean, the flagella is not beating; it's just showing the flow field as a function of the different angles. Okay, and then this analysis I'm just skipping for the interest of time. Now the next step, we wanted to see the interaction between different swimmers. So for that we needed a physical flagella so that the other flagella can come and bend it. And it turns out that if we still have the point force approximation, then the flow field that is created is actually quite different. So that's why we started to putting in more details. So right now we have a physical flagella which is modeled as a slender rod. We distributed the active forces as a series of Stokes laws about it. We incorporate the flow field created by the cell body, flow field created by the movement of the flagella, and they couple to each other. And also, if there is another flow, then the disturbance flow created by this extended nature of the cell body has also been incorporated. So these are the set of equations. I'm not going to go through in detail, but just to point out that these blue terms are the flow field terms, which are actually enormous. Okay, each one of them is an enormous term. Okay, so apart from that, we have the spring constant that actually tries to restore the flagella to its original orientation, the axisymmetric orientation. So the K value, if it is small, then it's quite flexible, and if it is large, then it acts like a rigid object or maybe the axisymmetric object. Okay, note that the axisymmetric object is still head-tail asymmetric. Okay, so yeah, so this is the result. This is the earlier simple-minded flow field, and this is the complete flow field, and you can see that there are differences. Okay. Anyway, so now coming back to the original question, we put the swimmer in a flow. Okay, this is taken to be a Poiseuille flow, which is typically created between two flat plates, and I mean, we do not incorporate any effect from the boundaries. We just have the flow, and then therefore our results will be valid only sufficiently away from the boundary. Okay, so once we've put that, this is like the Raphael's experiment. Okay, so now we see this kind of thing. So instead of now we don't have any orienting field or no light source, for example, but still you see if the swimmer starts a little bit away from the center line, then they actually oscillate and then go towards the wall, go towards the high shear rate region. That happens even without the light source. And then if you come closer, then and then the oscillations are big enough, I mean close enough so that it crosses the center line, then the amplitude of the oscillations grow, and eventually the amplitude will be half amplitude will be so large that it cannot come back anymore and then starts tumbling and go away. So eventually in this case also it will go towards the wall. Very few instances where the swimmer starts very near to the center, their oscillations are damped, and then they are trapped to the center line. Okay, that's the observation. We see sharp cross stream migration toward even without light. Okay, that's the observation, and this is strikingly different from what is observed earlier for active systems but symmetric that I talked about. Even for passive systems or asymmetric cases, it's not observed. You can see that largely the trajectories are flat. So the key aspect is activity plus asymmetry. So we wanted to understand that. So we took this rigid limit, and we assumed that during one oscillation the height is more or less constant. Okay, and then in that case we can simplify the equations and come up with this theoretical plot. This is theta dot, the angular velocity versus theta. So you can see that from here to there, the particle is actually orienting upwards on an average. From here to here, it's orienting downwards. And this asymmetry, which is related to the head-tail asymmetry, causes the particle to be in the upward direction more on an average, longer on an average than the downward direction. And that is the reason why you see the upstream, so the cross-stream migration towards the wall. This is theory. This full simulation looks like that. Then you can see that the heights are a little bit changing, as you can see from here as well. So, but the plots, these are from the full simulation. They are, I mean, qualitatively they are similar to these, as long as the swimmers are fairly rigid. If the swimmer is actually very flexible, then you deviate a lot, but still the time that is spent from here to there is larger, even for this one. Okay, so I mean, we believe that this is the fundamental reason. The head-tail asymmetry is a big factor, and it has a rich dynamics. I mean, even for these oscillations, we can see the oscillations here. It's growing, and eventually it will peak. Yeah, so it will start tumbling in this one direction and will go to one of the walls. That is as seen from the left frame. This is as seen from the center of mass frame. You can see that the oscillations start slowly and then grows, and then eventually it tumbles. Okay, so this is a damped trajectory. The oscillations are very small, and they eventually acquire the upstream direction. So in this case, the flow is that way. So there is a fixed point at upstream direction at the center of the channel. Okay. So we can understand that by clearly. I mean, so if you have a spherical cell body, like has been studied earlier, there is Stokes reversibility that is applied, and you can use the argument from there to show that the oscillations will be actually not growing. I'm talking about this now. Okay, so if you have such things, and it will actually oscillation would have the amplitude would have not changed with time. But the head-tail asymmetry breaks this Stokes reversibility. And then, I mean, in one simple way you can understand the growing amplitude is that when the swimmers are able to cross the center line, on the upper half, it tries to go to the upper plane. In the lower half, it tries to go to the lower plane. So therefore, the oscillations actually grows, the amplitude grows, and eventually it can go escape towards one of the walls. Okay, so if you're very near to the center line, however, it's actually the dynamics becomes very different. So we did a linear stability analysis, and then we actually showed that there is a fixed point. Okay, like has been discussed earlier. This is the phase-phase diagram, and then we also I do not have much time, so I'm just skipping. So we did the phase-phase limit cycle, but I want to actually, there are some control parameters. So it turns out that if we increase the average shear rate, that increases the population that is stuck to the center. And we can have a simple-minded calculation from our theory. It predicts about 22% of the population that is stuck to the center when this ratio is 16. And then if you change the ratio a little bit differently, then 30 to 40% can be trapped. Okay, so now just 1 minute or 2 minutes, I'll take this example. So now we put on the light, there is an extra torque now, okay? And this angle is theta naught. So in Rafai's case, in the earlier case, theta naught was pi, okay? So theta naught was pi, and this was studied. And then we saw that the particles actually accumulated near the center. And those are the, so this is the spherical cell body that was studied earlier. Those are the plots for that. And if you have head-tail asymmetric swimmer, you can see that again, they are also spoke focused, okay, toward the center line. It takes a little bit more time, but I mean, they do focus on the center line. But what is interesting is that now, if you change the orientation of the incoming beam, so this orientation if you change, then something interesting happens. So this is the kind of the phase diagram for that. So if the orientation is within these two quadrants, then there is no stability. So ultimately the swimmers move towards the light source, while small population actually stays into the other plane. But if the orientations are in these quadrants, then you can tune the quadrants to have the fixed point at a given height from the center line. You can actually tune the height at which you want to focus your bacteria. So there are possibilities, and I don't know much about the experiment. So I mean that's an advantage for me. I can imagine anything. Something could be actually rubbish also. But this is what we imagine, that suppose you put the light source in such a way, in both ways, both up and down direction, and suppose there is a detector which allows the, yeah, I will be finishing after that, which allows the bacteria to pass through. Then suppose you turn off one of the light source, so these will be focused at a height which is larger than this width, so the bacteria will not pass through. But if you turn on both of them, because of the symmetry, because both of them will try to do the same thing, so ultimately the bacteria will be focused at the center and they will pass through. Okay, this is just an imagination, possibilities. I mean, that mimics something like a living transistor. Okay. Okay, so there are interesting things, just one, okay, 30 seconds maybe. So we also did the pair dynamics, and then we saw some interesting behavior like that shown in this experiment. We saw this swirling around, and then we have some collaborators who produce similar kind of particles, active particles, that they also have this orbiting orbits. Okay, so so just concluding, so we are now looking at the continuum limit. I mean, so this will be very similar to the work from Frank and his collaborators, and also some reminiscence of the work by Sriram and others. Okay, so I mean so this to the end, I mean, this feels like a homecoming, because when I went out of the group, I went really Stocksian, and it felt nice to see Sriram's the sedimenting work, to see that okay, he was also doing the same thing in his early career. Okay, so with that I conclude. This is some of my other works in my group going on. So yeah, I end here. Thank you for your attention. Yeah.
What were the in the last slide you had this experiments by Pujala. What swimmers are these?
So these are actually photoactivated catalytic swimmer. So usually genus particle have half of the sphere chemically coated. Here only a spot is chemically coated, and then you activate with light. So when light source is there, it activates. Okay, I mean they are playing with shapes now, different shapes, and then similar things are going on. I mean, we believe that this because of the head-tail asymmetry and non-axisymmetry of the model.
More questions. So well, yeah, back.
Yeah.
If I consider two bacteria swimming, they form some kind of bound pair. Do I expect to see that?
Form what?
Will the bacteria swimming close by, will they form a bound pair?
Bound pair, yeah, that's what we see here. I mean, I did not have time to show. Yeah, so I mean, here you can see that they will actually keep on rotating in this manner. Okay, so if there is no other bacteria to disturb them. But I mean, now we are going to the dense suspension. We are actually trying to formulate something like Sriram's work, which I call the homecoming. And then hopefully we'll be able to see some kind of rotation, at least for our swimmers.
Would I be able to use some formulation similar to BCS, some Cooper pair thing to?
Okay. Okay. So yeah, I don't know about that. Okay. So yeah, there could be analysis. Okay, but I'm not so sure.
So I had a question. So for E. coli, at least the orientation of the flagellum with respect to the cell body happens because of the interaction between multiple helical flagella, which I imagine will make it quite stiff. So in the stiff versus soft limit of this angular stiffness, what did you use for these?
No, even E. coli flagella, I mean, they are not very stiff in the sense that if you have many of them, I saw indirectly, these are not reported, but I saw indirectly from Berg's movies. I mean, there are slight bends of this. It's not, maybe not at the joint, but there are gradual bends. Mm-hmm. This might be the first-hand approximation of that.
Yeah, I mean, in your top right picture here. So that's the flexible case, and sort of the flow. I mean, the curved orientation is producing a given motion, and the flow it generates in each case is self-consistently keeping the flagella bent.
Exactly. Yes,
I see.
Right,
okay. All right.
Yeah.
Okay, right.
So it,
okay.
yeah,
Nice.
that's the case.
Yeah. Okay.
Okay, there are no more questions. Thank you.